This video is on the metal semiconductor diode, also known as the Schottky diode. What we're talking about here is basically the junction between metal and a semiconductor. And we're going to choose a semiconductor whose higher energy electrons in the conductor band are higher energy than those in the metal. What that means is that the probability of finding higher energy electrons in the semiconductor is higher than the probability of finding higher energy electrons in the metal. And the Fermi level, which is an indication of that probability, is therefore higher for the semiconductor than for the metal. So when we see these two pieces and they're separated apart, what we see here is that the Fermi level of the semiconductor is higher than the Fermi level of the metal. Here in the semiconductor is an N-type material, so that it's doped with donor impurity atoms that donate lots of electrons. So the probability of finding electrons is higher than finding holes. As a result, we see that the Fermi level is closer to the conduction band. In the metal, there's no band gap needed for electrons do not need to overcome a band gap to enter the conduction band. So there's no band gap. So what we see here is that we have a very high concentration of electrons at the highest probability point. And as energy increases, we're going to find an exponentially decreasing number of electrons that are going to have that energy. And what we're saying is that the highest energy level electrons in the semiconductor are higher than those in the metal. So when we connect these two pieces together, what we're going to see is that these very high energy electrons here, there's a higher concentration of them in the N-type material than in the metal. So those electrons are going to diffuse into the metal. So as they diffuse into the metal, and now we look here at the band diagram when they're connected, as electrons then go on to the metal, they leave behind basically a region that is depleted of charge. So this is the depletion region that we have here. And that's because as electrons diffuse away, they basically leave vacant spots. Well, the other thing that happens is as electrons leave, the N-type material loses negative charge, so it becomes positively charged. So as this process of diffusion continues, this built-in voltage increases and increases to such an extent that it at some point opposes and keeps other electrons from diffusing. And we can see this here. Leftover electrons on the N-type of the material at some point see such a negative charge on the metal that they're basically held back. They're repelled and held back. So what we have here is basically diffusion will happen until this built-in voltage opposes and stops diffusion. Another way of saying that is that leftover electrons will now have to overcome this electric field in order for them to cross. And that overcoming that electric field is like saying they need to overcome an energy barrier. So they need to overcome an energy barrier for them to be able to cross. Okay, let's remove markers and then go to the next point. And the next point here is what happens when we apply a reverse voltage. And by that, we mean a voltage that basically reinforces the built-in potential. So let us remove the grounds here and let us then apply a voltage that reinforces that built-in potential. Well, when it reinforces that built-in potential, what that does, it increases the barrier. And that means that electrons now have to overcome an even higher barrier for them to cross. So those electrons do not move. So there's no conduction, there's no dopant carrier conduction. However, we do have some thermionic electrons on the side of the metal that they see a positive charge on the other side, so they conduct in the opposite direction. So that establishes some reverse current. This reverse current is not very high, however, because the thermal energy that is available is not sufficient to generate so many thermionic electrons. Nevertheless, we still have a reverse current. So let's remove markers and consider the opposite situation. What happens when we apply a positive voltage, a forward voltage that basically opposes this built-in potential, opposes the barrier. So if it opposes the barrier, then what we're saying, it reduces the energy barrier that electrons need to overcome to cross. So what we have here is that the barrier, it's now lower, and we have an exponentially increasing number of electrons that now are free to diffuse and cross the junction. So we have a forward current that increases exponentially with voltage. In summary, what we have is low reverse current and high forward current. So we use an arrow-like symbol to represent this diode. And the arrow points in the direction of the high forward current, which is the result of a positive voltage from the metal to the semiconductor. We do put a blocker here to indicate that reverse current is very low, and ideally zero. And then we put flares here at the ends, and that's to distinguish the Schottky diode from the PN-Junction diode. So behaviorally, what we're saying is that the Schottky diode is the same as a PN-Junction diode, where the forward current increases exponentially with forward voltage. But there are some differences. First, we have fewer charges crossing the junction. First of all, we don't even have holes crossing the junction. So if we have fewer charges crossing, we have a lower built-in electric field and a lower barrier. With a lower barrier, that means that we need a lower forward voltage to carry a particular current. In other words, Schottky diodes usually drop a lower voltage than PN-junction diodes. We also have that metal avails more thermionic electrons than semiconductors. So reverse current is slightly higher, can be higher. But we have no holes diffusing from the metal. The metal has no holes, so the semiconductor electrons do not recombine. Plus, holes do not diffuse into the semiconductor. That means that basically there's no forward transit time needed to reach the metallic contacts. In other words, the diffusing electrons almost immediately reach the metallic contact. And what that means is that in the depletion region, there is no diffusion, in-transit diffusion charge, because the charge just almost instantly gets to the contact. And that means that there's no effective capacitance holding this in-transit charge. It also means that when we recover the reverse condition, we don't need to recover that in-transit charge either, so there's no reverse recovery charge. In other words, the Schottky diode is faster than the PN-Junction diode. So designers like the Schottky diodes for those two reasons. First, it drops a lower voltage, so it dissipates less power. And then it requires less time to respond. The caveat here is that it does have some higher leakage current in the reverse direction. So that's the trade-off. I hope this video was helpful. Thanks for watching.